All right, so here we are. It's the final lecture in the course, lecture 34, and we are just reviewing the material that's going to appear on midterm 3 on Wednesday. So you can also look at the practice midterm that's up on the module for this week. It's the first item in the module, and it will tell you a little bit more information than this. It tells you all of the chapter sections that we cover. Basically chapters 5, 8, 10, and 11, but only select sections. And it gives you a few more details. There's something a little bit different about this midterm, and that is that it's open textbook. So you can make a formula sheet if you want, if it helps you study, but you also are allowed to just access the textbook during the exam. It's also a little bit longer than the previous midterms. First one was 50 minutes, then 60. This one is 75 minutes, plus you have 15 minutes for uploading your work. All right, so the midterm covers these topics, and we'll go through an overview of those, and then at the very end, we'll talk a little bit about the project presentations, and I'll remind you to fill out the spot survey before December 10th. Okay. So the very last piece of chapter 5 that we studied in homework 9 and quiz 9 was a statement of conservation of energy. So we took the Bernoulli equation basically and added 2 terms, right? So this is these terms on the left-hand side here, plus the first 3 terms on the right-hand side are the Bernoulli equation, and then we added a shaft work in and a loss term, right? We can also rewrite this alternatively as a head loss term. It has units of pressure, right? And then just reminding ourselves these little conversions that we're going to use all the time when we deal with these energy equation problems, that the work in per unit mass is the same as the work per time, capital W dot, which is power, right? So capital W dot has units of horsepower or other terms of power, divided by m dot. Our loss term is the internal energy and the heat, Q, added to the system, right? And then this little q, the heat per unit mass, is related to the net heat in, the net rate of heat addition, divided by m dot, or mass flow rate. Right, and then our shaft work term here, our head loss, shaft work head loss, HS, is just our shaft work per unit mass over G, the gravitational constant, right? So this is all just a statement of conservation of energy. It says the rate of change of the energy, the total energy in a system, like the system we see over here on the right of the screen, is equal to the net work done on the system plus the net heated added to the system. That's the only way you can increase the energy in a system. Okay, so that's it. That's really, bird's eye view of the chapter 5 topics we're going to cover. So you'll have problems like, you have water being pumped from a lower reservoir to a higher reservoir. How much power does the pump supply to the system, right? And so you would use this first version of the equation, and then you would convert little w to big W using this equation here. Moving on to pipe flow, we see a lot of the same concepts that we just saw in the mechanical energy equation. In fact, we use the mechanical energy equation a lot to solve pipe flow problems. And that head loss term that we have here in equation 584 gets split up into major and minor losses for a pipe flow, right? So major losses, they're called major losses because usually they're the majority of the viscous losses, the majority of the losses, and they're due to friction viscous effects. And then minor losses are due to things like valves, elbows, fittings, exits and entrances to pipes. And a lot of times we have both major and minor losses in a problem, and it really comes down to finding the friction factor, calculating it, or the loss coefficient, and the loss coefficient, and then just using our average velocity, V, the length of pipe we're considering and the diameter of the pipe to go ahead and calculate our head loss terms. So let's take a closer look at major losses in a pipe. So now we have to make a distinction between laminar and turbulent flow. So if you remember, for pipe flow, the rule of thumb was if your Reynolds number is less than about 2100, you're in the laminar flow regime. It's greater than about 4000, you're in the turbulent flow regime, and in between is transitional. If you have a laminar flow, it's super simple. Your friction factor F that goes into that head loss term is just 64 over the Reynolds number. That's it, right? And the Reynolds number is here. It's just the fluid density, the mean velocity, pipe diameter over the viscosity, okay? If you have a turbulent flow, things get a little bit more complicated. You do have formulas. There's the Colebrook and Halland formula, but in practice, people tend to use a Moody chart to find the friction factor for a turbulent flow. We'll look at a bigger version of this on the next slide. What do you need to know to pick the friction factor off the Moody chart? Well, you need your roughness, and that depends on your material, right? So if you're given a problem and it says you have a galvanized iron pipe, you go over to table 8.1 and you see your equivalent roughness factor in either feet or millimeters. And you take that and you divide it by the diameter of the pipe to get your relative roughness, epsilon over D, and then you can use the Moody chart, right? So let's look at a bigger version of the Moody chart. So on the horizontal axis at the bottom, we've got the Reynolds number. Just a minute, I've got. And I have a question saying, is it okay if we use the formula always to find F? Yes, that's totally fine. Most people find it unwieldy, but you can absolutely use the formula. It's completely equivalent. It's actually probably a little bit more accurate if you use the formula, although accuracy in pipe problems is a far off goal. All right, on the horizontal axis, we've got the Reynolds number, but see, it's on a log scale. So each of these vertical lines corresponds to a power of 10. So just be careful, it's not a linear scale. Then on the left vertical axis, you've got your friction factor. On the right vertical axis, you've got your relative roughness, epsilon over D of your pipe. So what you need to do, first of all, is calculate the Reynolds number and understand whether you're in the laminar flow regime or turbulent. If you're in the laminar flow regime, great. You're just using this straight line. That's just your F equals 64 of the Reynolds number that we have for laminar flow. Done. If it's turbulent flow, you need to figure out how rough your pipe is by consulting table 8.1 from the previous slide. So you do that. Let's say you calculate that your relative roughness is 0.004. First, you come over to this right vertical axis and you find the line that corresponds to 0.004, right? And here we go. Now, if you also know the Reynolds number, let's say it's 10 to the 6th, you just trace the line back to where it intersects the vertical line that corresponds to the Reynolds number of 10 to the 6th. And where they intersect, you now stop and trace that back horizontally to the left vertical axis to pick off your friction factor. So now what do you do if you calculate your relative roughness and it's some in-between value, right? So what if your relative roughness is 0.005, but there are only lines for 0.004 and 0.006? You know, you just do your best. You could interpolate. You could find the solution for your Reynolds number for 0.004, find the solution for your Reynolds number for 0.006, trace those back, get the two corresponding Fs, and then interpolate. Or you could just eyeball it. Honestly, when we're dealing with pipe flow, 10% error is really reasonable. And that's because a lot of these values are just experimentally derived. Moody chart is in the back. If you have a hard copy, it's in the back of your book. Otherwise, it's sitting in chapter 8 as well. All right, so again, we've got major losses in pipe flow and minor losses. We just talked about the major losses due to friction. What about the minor losses due to fittings and pipe components? Well, there are all sorts of potential pipe components that you could have loss due to, right? And these are just basically scattered throughout chapter 8 in a bunch of figures from like figure 820 all the way up to through, I think, figure 835. You know, you just have chapter 8 open and bookmarked. But what you need to know to calculate the loss is just your coefficient KL. And if you have multiple pipe components, let's say you have a loss due to an entrance, a loss due to a 90-degree elbow, and a loss due to an exit condition, you just add those up, right? So your overall K sub L is the sum of the 3 individual ones. And I just got another question here, just a moment. It says 8.1 did not give a specific epsilon. Will we have epsilon in the problem? So you're talking about the homework problem 8, first problem. It was a pipe flow problem and it didn't give a specific epsilon. Okay, that's a really good point. They may not always give a specific epsilon, but often they'll tell you the material, right? So if we skip back to that table here, table 8.1, this is really important. Even if it doesn't give you a roughness, if it says your pipe is made of concrete or drawn tubing or cast iron or riveted steel, you know the roughness.
Yeah,
right?
but the roughness here is not a specific number. It says for the first one from 0.003 to 0.03.
Oh, I see. Yeah.
Yeah.
So in right, that's a really good point. So in that case, well, first of all, I promise you on the exam, I won't give you one like that that's ambiguous. I'll give you one where there's a definite answer. But in that case, I would just take the average. But once you know the material, you know the equivalent roughness, you can divide it by the pipe diameter and you're good to go. But good point. Okay, so if you imagine now that you have a large tanker reservoir and your flow is entering your pipe from that reservoir, that entrance could be shaped in a number of ways. Somebody could just stick a pipe into the reservoir and it's jetting inside like we see on the top left, and that's associated with a relatively high loss, a coefficient of 0.9. It could be just a square shape like we have on the top right, and that's a loss coefficient of 1/2. Slightly rounded on the bottom left does much better. Your loss coefficient is just 0.2, and then well rounded, your loss coefficient drops by an order of magnitude down to 0.04, right? So if you have language in your problem like the entrance is rounded, the entrance is sharp edge, you know, you go to figure 822 and you pick off your K sub L, your coefficient. I won't give you a problem like this on the exam, but you may run into problems where you have a very specific radius of curvature and you can pick off a very specific loss coefficient K sub L, right? So it's actually a continuous function of the radius of curvature for a rounded entrance, and you can find that in figure 824. Exit loss coefficient is always 1, no matter what. No matter if this is curved, sharp, you know, slightly curved, well curved, no matter if it's a nozzle, loss coefficient is always 1 for an exit from a pipe, no matter what. And I don't know how to refer to this figure. It doesn't have a number in the book. In the paper copy of the book, it's on page 436, but that doesn't do you much good. Okay, we can have a sudden contraction. And here the loss coefficient is just a function of the ratio of the 2 cross-sectional areas, the pre-contracted and post-contracted. And you just have to calculate that ratio, go to figure 825, trace your number up to the line. When it intersects the line, trace it left to the K sub L axis and find your coefficient that way. Same thing with a sudden expansion. Calculate your ratio of areas, trace it up to, let's say it's 0.4, trace it up to the curve. When you hit the curve, trace it to the left over to the K sub L axis, pick off your number. So this is kind of interesting. The really high loss is associated with bends. So you see this flow going through this 90-degree bend here. And the reason that the losses are high is that when the flow has to turn a sharp corner like that, you'll get a little bit of recirculation. You'll get a little vortex swirl here in the inner corner. And if you were to look at your velocity profile, it'd be outward or forward pointing for the outer part of the pipe, but then on the inner part, you'd have a little bit of reversed flow. So that's a really high loss coefficient, 1.1. But one thing you can do to mitigate that is to install guide vanes. And if you do that, then the flow can stay nice and laminar with no recirculation zone, and your loss coefficient drops down to 0.2. It's in figure 830. All right, table 8.2 is wonderful. Basically a really long table. It's on the next 3 slides of all sorts of different pipe components. So 90-degree and 45-degree elbows, threaded or flanged. Your problem should tell you if they want you to assume threaded or flanged. Threaded has higher losses associated with it. So that's when the components actually are threaded and you have to screw them together. Flanged is when you can just sort of fit them together and they stick due to friction. You've got 180-degree bends and associated loss coefficients here. You've got T's here where you have flow coming in and meeting a perpendicular stream. And then you've got unions. You've got T unions and regular unions. And then you've got valves. And valves are often represented by sort of a circle with an X through it in a figure. And then, you know, your problem will say it's a globe valve fully open or a gate valve half closed. You know, you need some information about the valve to be able to pick off the correct loss coefficient. All right, so that sort of bird's eye view now of chapter 5, the energy equation or the mechanical energy equation, and then moving into chapter 10, pipe flow, right? So for pipe flow, we just did an overview of major and minor losses in the Moody chart. Does anybody have a question on the chapter 10 stuff? You know that you can stop me at any time. Or sorry, that was chapter 8, pipe flow. Okay, so now we are moving on to chapter 10. So the last 2 chapters that we're looking at this class have this really neat analogy. So first, chapter 10, we look at open channel flow. And so now we have basically pipe flow, right? We have flow in one direction, but instead of the flow being enclosed and the channel being completely full, we now have maybe a channel that's not completely full and the top is open to the atmosphere, or we just have a channel without a top, right? So any kind of river, canal, that type of flow. A lot of sewage flows are actually closed in pipes, but it's basically an open surface that's open to the atmosphere. So they're treated as channel flows. So there's this really neat analogy between these open channel flows and compressible flows. There's a really great analogy between the Froude number and the Mach number and hydraulic jumps and shock waves, right? Because it's basically the same physical phenomenon. So if you imagine you've got a pond and you throw a pebble into it, and that pebble creates ripples of waves that propagate out on the surface. They travel with a wave speed c. It turns out that that process is mostly driven by gravity, and we can derive that the wave speed is the square root of the gravitational constant times y, where y is the depth of the river or whatever body of water, right? So we'll talk about the Froude number in a moment, but basically when your flow reaches the same speed as c, the wave speed in that fluid, you start to have the incompressible equivalent of shock waves, which are hydraulic jumps, which most of you made in your kitchen sink a couple of weeks ago. So we derived for open channel flow the so-called Manning equations. So this equation here, 1016 for velocity, this is for average velocity is what you're calculating here, and 1017 for volumetric flow rate. And it depends on this constant kappa, which is kind of funny. If you go over here, kappa is just 1 if you're dealing with SI units, but if you're dealing with BG units, it's got a value of 1.49. And then you got Manning's coefficient n, which is tabulated. I actually didn't include it in the slides, but I believe it's table. Let me look, look before you quote me on this here. want to say table 10.1, but I don't want to be wrong. It is. It's table 10.1. So values for n, the Manning coefficient, are tabulated in 10.1. And again, it's got, you know, natural channels, floodplains, excavated earth, clean, gravelly, weedy, artificially lined channels, glass, brass, steel smooth, steel painted, etc. So basically, you'd have to be given some information about the material that the channel is made of, and then you can pick n, the Manning coefficient, out of table 10.1. So please make a note of that, because that's something I'll put in the slides. Okay, so once you've got that, you need to calculate the hydraulic radius. Now, the hydraulic radius is not just a measure of a span of the cross-sectional area of the channel. You actually have to calculate the area and divide by the perimeter. And it's not just any perimeter, it's the wetted perimeter. So if we look here on the bottom at these figures, and we're looking on the right figure, we've got an open channel flow, and we're looking at a cross section. So the flow is into the slide, into the page. The wetted perimeter is indicated here by this dark arrow. And here it happens to coincide with the perimeter of the channel. But if the channel were not completely full, right, if the water level were lower than the top edge of the channel, it would just be the perimeter of the part of the channel that's filled with water, just the wetted perimeter. It's very important. If you take the perimeter of the whole channel, you'll get the wrong answer. We also don't include the free surface as part of the perimeter, right? So it's just the sides that are wetted. So that's P, and then A is just the cross-sectional area, again, of the fluid in the channel. Using those, you just divide them, you can calculate your hydraulic radius. S naught is the bottom slope. So if you have a channel at an incline, just the slope of that, you know, you can take two elevations and divide by the distance between them to get S naught. Often it's just given as part of the problem. You also need that in your Manning equation. All right. Oh, here I do have table 10.1. Never mind. So here you go. Here you see the values of the Manning coefficient, and for different types of natural on the left, and then artificially made channels on the right. Ranges from about 0.01 up to 0.15 for trees. Okay, now getting into the Froude number. So this is a really fascinating part of open channel flows, going back to this analogy with shock waves. So the Froude number is V, the velocity of your fluid flow, over C, the speed that a wave travels on the surface of that fluid. So if normally, the normal situation is your Froude number is much less than 1, and the waves travel much faster than the fluid itself is traveling. But if the flows become the same speed, then a wave can no longer propagate away from the fluid flow. It can sort of get stuck. Imagine the fluid is flowing this way, the river is flowing this way, and a wave from a pebble is trying to flow in the opposite direction. Well, if those speeds are the same, that wave gets stuck in one location. So if you're looking at it from the shore, it's not moving, right? What happens if another wave comes again? It gets stuck in the same location. They can build up and form a hydraulic jump. So as long as the Froude number is greater than 1, so the river velocity, or, you know, the channel velocity is greater than the wave velocity, you can get hydraulic jumps, right? So just looking at this classification, for a Froude number less than 1, it's not possible to have a hydraulic jump. And then you see these different categories for different ranges of Froude number. You could have a standing wave, weak jump, oscillating jump, etc., based on your Froude number. If you look at this figure in the top right, down upstream of the hydraulic jump, we've got condition 1, and downstream of the jump, we've got condition 2. And the important parameters for a hydraulic jump are the depth upstream, Y1, and downstream, Y2, and the Froude number. So two equations that we derive that we use all the time for hydraulic jumps are calculating the ratio of depths before and after a jump. And all you need to do that is the Froude number. You can also be giving one of these, Y2 or Y1, and the Froude number and calculate the third missing quantity. And then, oh, this little guy needs a L. This is the head loss term, H sub L. So you can also calculate the losses, the viscous losses due to the fluid passing through a hydraulic jump. If you remember talking about the hydraulic jump in your kitchen sink, the reason that the water has to make that jump from a very thin sheet when it comes out of your kitchen faucet to all of a sudden jumping up to a very thick sheet is by conservation of mass. It has to slow down by the time it hits the walls. And the only way it can decelerate fast enough is to increase its cross-sectional area and also experience viscous losses because of all the churning around that happens at the jump. So there's a head loss associated with that, and you can calculate that using equation 1027. Please draw, if you're annotating on your slides or if you're following along on the slides, please draw a little L here. I'll fix that and repost the slides. And now to calculate the head loss, you need all three of these quantities, though. You need the upstream and downstream heights or depths of the flow of fluid, and you need the Froude number upstream of the hydraulic jump. All right, so that's a bird's eye view of open channel flow. We talked about the Froude number and how when you have this critical situation where the fluid flow suddenly has the same speed as a wave flow, you can start to get waves building up at the same location and get a hydraulic jump. Well, in compressible flow, you can have the same phenomenon happening, a wave pile up, this time it's sound waves, and you can get a shock wave, right? We'll talk about that in a couple of slides. First thing, first important topic in chapter 11 is just the stagnation properties for isentropic flow. So if you remember, isentropic means that the entropy is not changing. Entropy is not increasing, so that means that there's no heat added and it's a frictionless process. So we have a way to relate in a flow the stagnation temperature to the static temperature, and it's a function of the mean velocity and the specific heat at constant pressure. Then we've got the ratio of stagnation to static pressures, and that depends on the previous equation, that ratio in the previous equation, raised to K, the ratio of specific heats, Cp over Cv. And then we've got an expression as well for the ratio of the stagnation density to the static density. And that also depends on the ratio of the stagnation temperature to static temperature. These are the equation numbers here. And this comes in handy a lot if you're dealing with, let's say, a shock flow problem, right? So you've got a standing normal shock, you've got upstream of the shock and downstream of the shock. Often you need to be able to relate on one side of the shock or the other. You need to be able to relate the static and stagnation properties. And these relationships allow you to do that. It's even more handy to have these relationships in terms of the Mach number. So if we do that, we take these relationships and we do a bunch of manipulations to them, we can rewrite them in terms of just the Mach number instead of the velocity. And here we've got these three ratios, and now they're a function of K, the ratio of specific heats, and the Mach number, and that's it. Let's talk about the Mach number a little bit. So just like for the Froude number, we've got the flow speed V over C. C is also a wave speed, but now it's the speed of the sound wave that's propagating. And we can show that the speed of sound for a compressible ideal gas is the square root of K, the ratio of specific heats, times R, our gas constant that's tabulated in tables 1.7 and 8, and T, the static temperature. Be very careful to always use the absolute temperature. So Rankine or Kelvin, depending on what unit system you're using. So a couple interesting things here. If you look at this figure on the top right, if you look at the value of the ratio of specific heats for helium versus air, we see that K is a little higher in helium. So the speed of sound travels faster in helium, which I think we talked about it last time, that's why if you've ever, inhaled helium from a helium balloon, that's why your voice sounds so funny, right? Because it's got a higher ratio of specific heats. Okay, I have a question in the chat, and it says, is 1152 supposed to be rho naught over rho? Yes, it is supposed to be rho naught over rho. I copy pasted this equation from the textbook. That's a typo right from the textbook. So sorry about that. That is rho naught over rho. I will fix that as well and re-upload the slides. Thank you for that catch.
Can I ask you, please?
Yes, of course.
So we said that only if we have the K is 1.4, we can use the appendix D, to find one of these ratio.
Yes.
So what about if we have 1.4, we still can use this equation to find any ratio?
You can still use the equation, yeah. If it's not 1.4, you have to use the equations. If it is 1.4, you can either use the charts or the equations.
Okay, thank you.
You're welcome. All right, so we can, as we just said, we can either use these equations, and these are good for any ideal gas, whether K is 1.4 or a different value. If K is 1.4, we can use figure DI or table DI from appendix D. So I'm going to zoom in just a minute on that. But first, let's talk about the Mach number a little bit. So this is just a visual depiction of sound waves building up. So here we have a pebble dropped in a pond, and it's letting out ripples on the surface of the pond, and the river, the pond below it, is not moving. Here we have a current in the pond, and you start to see some asymmetry in our ripples. Here, the current speed is the same as the wave speed, and this is, I'm using a Froude number analogy because I'm talking about ponds and open channel flows, but if we're talking about compressible flow, this is a Mach 1 situation. And then for a Mach number greater than 1, you actually get these circles that start to be swept back. And here's some nice oblique shock waves visualized here. Okay. So here is figure DI from appendix D. This is only for isentropic flows for air and oxygen, basically, that have K of 1.4. So on the the horizontal axis, we've got our Mach number. On the left vertical axis, we've got our stagnation and static ratios. And then we've got 4 different curves, and we just have to pick the right one depending on what we're interested in. So we'll ignore A over A star for now. That's for a converging, diverging nozzle. A star is the smallest cross-sectional area. It's called the throat for a converging, diverging nozzle. We'll ignore this one for now. So let's say we're interested in T over T naught. This is our curve. We know our Mach number. Let's say it's 1. We trace it up to intersect the line for T over T naught. Where it intersects, we trace it back to left axis, and we pick off our value of T over T naught. Here it's about 0.84. Right. All right. So we just looked at how to relate static to stagnation properties. We can also write down really similar relationships for the properties across a shock wave. So here's an actual normal shock wave visualized with Schlieren imaging. Then in the middle on the right, we've got a depiction, sort of a cartoon of a normal shock wave. The upstream value, so the flow is left to right. So upstream to the left of the shock, we've got all of our static and stagnation properties, and they've got a subscript X. X stands for upstream. Downstream, we cross the shock, and now we're at the downstream portion. And now our downstream properties have the subscript Y. Okay. we can derive this set of equations that relates the properties upstream and downstream of the shock. So here we can, if we know, and all in terms of the upstream Mach number. So here, if we know the upstream Mach number, MAX, we know the downstream Mach number. If we know the upstream Mach number, MAX, we know the ratio of static pressure before and after the shock. Third equation, again, just given MAX, we know the ratio of temperature, static temperature before and after the shock. Fourth equation, this is really interesting. The one quantity that does not change across a shock is stagnation temperature. And then our final equation here, we can calculate the ratio of stagnation pressures across the shock, again, given only the upstream Mach number. So it's interesting if you look at what happens to certain quantities when you cross a shock. If you look at the velocity and the Mach number, they slow down. You lose energy, right? When you cross a shock, you lose energy. Kinetic energy gets translated into heat and loss, right? So what does that mean? That means when you cross a shock, your velocity goes down, but your pressure goes up, your density goes up, your temperature goes up, your loss goes up, your entropy goes up, right? If it's not an isentropic process, right? So just to have that intuition, you should understand that a shock is, again, in analogy with a hydraulic jump, just like we lose energy and we have dissipation, energy loss to dissipation as the flow goes through a hydraulic jump, we have energy loss to dissipation as the flow passes through a shock wave. We have a wonderful figure. I've only put the figures, but there are corresponding tables as well if you prefer to interpolate over eyeballing figures. Here, these now are the ratios of the properties across a normal shock wave. We've got the upstream Mach number on the horizontal axis. We've got all of our ratios, or many of our ratios on the right vertical axis, and then two other ratios on the left vertical axis. So again, it's just a matter of finding which curve you're interested in, finding your Mach number, tracing it up to your curve, and then tracing it back to either axis. Again, this is only for k equals 1.4. All right, last topic I want to talk about is what happens when you have compressible flow in a duct. Now, this is kind of mind-boggling because throughout this whole course, we said, because of conservation of mass, if I have flow through a pipe or a duct, if the cross-sectional area gets smaller, the flow accelerates, right? We know this, right? Turns out for a Mach number greater than 1, that's no longer true. We get the opposite behavior. We have compressible flow. Remember, the dividing Mach number between incompressible and compressible flow is a Mach number of about 0.3. So for a Mach number of about 0.3 and below, we can ignore compressibility effects. For 0.3 and above, we have to deal with compressibility effects. So for a Mach number less than 1, the behavior is as our intuition is, right? We have a converging passage and our velocity increases. But now what happens for a Mach number greater than 1, our supersonic flow? If for a converging passage, our velocity actually decreases, which is totally counterintuitive. And it comes from this equation that we can derive. You can actually see what happens when Mach number is 1. We get a 0 in these parentheses, right? And that tells us that we get no change in velocity where we have no change in area. That implies that we can only have a Mach number of 1 at what's called the throat of a converging diverging nozzle, like you see here. And we can prove, we won't talk about it now, we can prove that dA is equal to 0 has to be converging diverging. It can't be diverging converging like we see in the middle. It has to be converging diverging. So it turns out the only way you can get supersonic flow in a compressible channel flow, in an interior flow for compressible flow, is with a converging diverging nozzle. That's why when you look at a rocket engine or any of, any rocket booster, anything that is meant to give hypersonic or supersonic flow, it always has a converging diverging shape, because Mach number 1 can only happen at the throat, the minimum area. So you have subsonic flow coming in, it accelerates because the area is getting smaller. Then at the throat, it hits Mach 1. Now the flow is sonic, Now, if you were to continue getting smaller in cross-sectional area, it would slow down. We don't want that. So we have a diffuser, we have a diverging area, and it accelerates the flow further. That's the only way you can get supersonic flow in a duct, is to have a converging, diverging nozzle. And that's why you always see this shape that we see here at the rocket engine for supersonic and hypersonic applications. All right. I want to leave a little time at the end for questions. I think I've hit all the main notes for chapters 5, 8, 10, and 11. Just some reminders, jump in at any time. Your quiz and homework are due tonight at midnight, but I was really nice. And instead of the usual, you can't see the solutions until your 10th attempt, because you don't have extra TA support, you know, Hyungun's office hours are over, and yeah, you could have gone Thursday and Friday, but who had time, let's be honest. I've set the homework 13 so that if you have one wrong attempt, it will show you the solutions to the problem. So that should help a lot. But if you still have questions, if that, you know, if you see you can't get the right answer, you see the solution, still doesn't make sense, I'm holding a half an hour of office hours tonight at 7 to 7:30. Here's the Zoom meeting info. Feel free to drop in. Be very happy to answer your questions. Feel free to email me. Feel free to email Hyungun. Okay, midterm 3 is this Wednesday, but it is open textbook, and you have a little bit of extra time on it, 75 minutes. Please do the practice midterm. You know, one of the best ways to study. I got a question in the chat. All right, is the extended time due to expected increased difficulty? No, I honestly don't think that the difficulty is more than midterm 2, but a lot of people weren't able to, even though midterm 2 is 70 minutes, I think, a lot of people were not able to finish midterm 2 on time. So this class is not about how fast can you solve a problem. It's about what do you know about fluid mechanics? Can you apply it? You know, that's my objective. So I made it 75 minutes. On the syllabus all semester, it said that your video project presentations were due tomorrow. They're not. They're due on Thursday. I had a couple of groups who ran into some problems and asked for an extension, and in order to be fair to everybody, decided to just push the due date back for everybody. So they're due at midnight on Thursday. Your presentation will be either this Friday, Monday next week, or Wednesday next week, the last day of class, right? It's going to be during the normal class time, 1:25 to 2:15. If you're in groups 1 through 5, you're going to present this Friday. If you're in groups 6 through 10, you're going to present on Monday, 11 through 15 on Wednesday. I got a question in the chat, just a moment. Are the group presentations going to be live in class or pre-recorded and then played during those classes? I actually left it up to you. If you go to module, this week's module, the very last item is basically the Zoom link to Friday's video project presentations, and I've got some instructions in there. And that's up to you. If you do pre-record it, you've got to get through presenting your single slide in about 3 minutes. And then you've got that 3-minute cap on your video. So if you do pre-record it, please cap it at 6 minutes, because we really have a hard stop of 8 minutes per group to stay on time. And if you cap it at 6 minutes, then that'll leave time for Q&A if other students have questions about your project, and also to switch to the next group. But you're also free to just do it in real time as well. What I say in the link for Friday is that I will make everybody in groups 1 through 5 on Friday a co-host for the meeting. So anyone in groups 1 through 5 is free to share their screen. Okay, another question. Question 1 on the practice test. Oh, okay, yes. So question 1 on the practice test has a pipe flow, and it's at an angle. And I'm actually going to put the question up in a second. Let me just finish up through the announcements here, and then I'll put that up. I think that's it. If you don't know what group number you're in, go to Groups on Canvas Video Project Groups, and it has the group number. And please fill out the spot survey, because it it helps me know what's going well in the class. All right, let me go to the practice exam. Okay, so here's this week's module. Here's the practice exam. Let's preview it. I know it looks a little different for me than it does for you guys because I'm in a different role in Canvas. Come on, you can do it. Oh, this is going to break my computer. Come on. It's hanging up a little bit. I think I actually remember the figure number from the textbook. Let me see if I can find it in the paper copy of the textbook here. Aha, here it is. All right, we're doing this the old-fashioned way because my browser is choking. Yeah. Oh, all right, let me get rid of my background on Zoom so you can actually see. All right. So we have a pipe and it's at an angle. And the question is this flow, can it be up the pipe or is it necessarily down the pipe? And the question is, it can be up the pipe if the difference in pressure is large enough that it overcomes the force due to gravity. So if we have a really large pressure at the bottom end and a much lower pressure at the top end, then that force due to the pressure could be enough to overcome gravity and make the flow actually be up the pipe. All right, I'm sorry, oh, here we go. All right, so can you guys see me sharing the practice exam? Are there any other questions about the practice exam? I got one more here. Okay, question 2, yes. So if you haven't taken the exam yet, you can plug your ears. So question 2 asks this question: if we have a flow between this section and this section, are the losses incurred major or minor losses? Well, we just talked about in our review how major losses are due to friction and minor losses are due to pipe fittings like bends, elbows, valves. Well, there are no pipe components between the two manometers, so the losses are due to major losses due to friction. Other questions?
I have a quick question.
Sure.
When you say you're dropping 3 of the homeworks and quizzes, does that mean 3 total or 3 of each?
3 of each.
Oh, wow. Thank you.
Yes. All right. So does everybody feel clear about, this is sort of your roadmap for the rest of the semester here. This is the last lecture today. No more homeworks or quizzes are due in the class. It's basically the midterm and the video projects. So if you go to the module and you click on the link to the video presentations, you'll see additional instructions. If you go to the practice exam, you'll see instructions for the exam there. Any questions? One more, let's see. Okay. All right, well, we kind of 2:15. If you think of additional questions, drop in on me tonight from 7 to 7:30. And other than that, I know everybody's super busy this week. Good luck with all your projects and all your studying. And I will see you guys on Wednesday and Friday.